Hello, I'm Ryan Friedman. I'm going to talk about ArduPilot and ROS2. So a little bit about me. During the day, I work at AeroVironment, working on autonomy. So I mostly work on ROS-based stuff, and ArduPilot's just for fun for me. But I like ROS a lot. And this picture here is about 10 years ago. How I got into this was flying motor gliders with FPV. And so yeah. So here's the agenda. Going to talk about some architecture and design goals. This stuff is mainly for the dev team because you don't know why we're building all the things we are in DDS and how we go about selecting which features to add. Then sort of a general progress update, what's next, some simulation and random tidbits on terrain navigation and plans and maybe a demo if I have time. So um, why would you use ROS to work on ArduPilot? I'm assuming most of you have heard of ROS. So it's basically an ecosystem of robotic tools to build autonomy. And it allows you to integrate with a lot of higher level features than is possible to run on the ArduPilot flight controller. So I'm an autonomy developer and I work on more platforms than just ArduPilot. And so one of the more difficult things for my job is writing an algorithm to do some behavior and make it portable to multiple vehicles, even between certain vehicle types to may say take off and go to a waypoint in global coordinates can be hard to do. You spend a lot of your time working on interfaces. So what I'm trying to do is make ArduPilot as easy as possible to work with ROS2 so that autonomy engineers don't have to reinvent all the other wheels. So examples being logging and data replay and benchmarking and testing and a lot of these standard things you need to do with robotics. There's a lot of great tools available in ROS, and I don't really want to build them all again every time I want to do some algorithm. So the main theme of this talk is how do we lower the barrier to entry for ROS developers to interface an autopilot with ROS2 compared to basically the existing approach of MavROS or MevSDK. And since I've started this, one of the things I've found that in doing this, it's made ArduPilot a really great teaching tool for people new in robotics. Once you know a little bit of ROS and you know a little bit about flight controller, you can sort of combine them and do some really fun, exciting stuff in not that much time. So if you don't have ROS, if you're a C++ developer, there's a couple ways to interface with ArduPilot right now. There's some Mavlink C++ bindings. There's MavSDK and MavROS. And using these is challenging because not all platforms use Mavlink. I know it's the most common one for the open source flight controllers, but a lot of the other platforms I work with use other communication protocols. It's a lot of work to rewrite a lot of these applications every time you want to port to a different vehicle. And ArduPilot also has a lot of great libraries in the libraries directory. They work really well on ArduPilot on embedded, but unfortunately they're not designed for reuse. So you can't say convert the AC fence into a ROS node and run that as your own geofence in a companion computer and add capabilities. So you do have to rewrite a fair amount of stuff if you want to do autonomy, but thankfully there's a lot of other people that are doing this in the industry that can provide you a lot of these basic tools. So that's all the stuff in the gray is sort of the areas that I work on. So you basically have this gray layer of all the applications you're developing. You have your communication layer, so it's Mavlink, or what I've built up is the XRCE DDS layer. And then maybe you can use REST to talk to your vehicle, as we've seen in another talk. There's a billion other protocols, and really you just want to be able to control the autopilot, which provides some awesome capabilities like determinism, but it is flash constrained and CPU constrained, so you can't develop autonomy on that for all scenarios. So what are we trying to do in the ROS interface for ArduPilot? And how do we accelerate development? Well, the first thing is just provide a bunch of really great tooling for building things. We want to provide some mapping engines. So maybe it's 2D mapping, which is nav2 cost map is people on rovers might be familiar with that. There's a lot of different control models that you can use for higher level controls or even low level controls off board. Tons of planners. There's this great library called OMPL, which has probably over 30 or 40 different planners, open source. Researchers much smarter than me have already written all those. So I'd rather not have to read a research paper and spend a bunch of time trying to implement RRT star or, whichever planner. You can just import those and use them. So tons of state estimation stuff. Fuse is a new library that's being adopted for doing 3D fusion. And one of the big things for me is there's a really active community in ROS. Just like the ArduPilot Discord, there's another Discord for ROS. And there's tons of really passionate, awesome people who are always willing to help you develop autonomy. And two of the other things for companies looking at doing autonomy, ROS provides, it's commercially backed, so it's maintained, and it's certifiable to certain standards. So for me, some of the big things that are missing from ROS, from the ecosystem, are swarming. There's no deployment capabilities for taking your C++ code and putting it on a Raspberry Pi. That's nice. The 3D development tooling is not really existent except for simulation. So visualization is hard right now in 3D. And then simulation for large outdoor environments, I haven't really seen any open source tools that can do well yet that scale. So I'm not going to go through all the design goals, but if you're on the dev team and you're wondering about why we're doing things the way we are and why we don't care about using doubles for everything, even though that ArduPilot stores them with far less bits, it's because we just want to make it easy to use. So we're using common messages and consistent coordinate systems. So you don't, as a ROS developer, you don't have to go check the Mavlink spec to see what frame your altitude is in and whether it's in centimeters or meters or, all that stuff. It's just all SI. So it basically lets developers get spun up faster and try documenting everything as best we can. One of the things we don't have to worry about that Mavlink implementations did was the latency with low bandwidth between the ground station and the vehicle. So when we put a companion computer on a vehicle, especially if you have Ethernet, bandwidth is basically not a concern anymore. So we can use a lot more data to make things easy to work with and still keep our latency pretty low. So there's a couple other, there's other flight controllers that implement a ROS interface, but they don't have ABI stability. So we're trying to maintain ABI stability. So every time we have a new release, we don't break all your applications. And just try to keep things, principle of least surprise or whatever that's called. So unfortunately, this is very qualitative, and I don't really have any way to grade work on if we're actually meeting these goals. But I think generally it's feedback from other developers. If the ROS developers say that ArduPilot's easiest to work with, then that's a good thing. If people start extending ArduPilot and adding their own messages, that's great. And if newer developers can replicate the examples without filing 18 GitHub issues on how do you compile it, that's also great. So just a little note on ArduPilot SITL. If you're a ROS developer and you're wanting to develop ArduPilot or develop autonomy, I think ArduPilot SITL is the best technology out there right now for developing autonomy. SITL provides a huge amount of customizability and it can run very, very fast. So I've started using this internally to basically develop autonomy behaviors using SITL as a way to test my code in a much more capable way than we could with standard things like G-test mocking. And it's really nice because if SITL can run on an STM32, it can run in our CI. At least I hope so. So it's been really nice to be able to run with higher speeds and be able to test more scenarios for autonomy behaviors. So things that are treated as edge cases and require manual testing can now be automated pretty quickly through the use of SITL. And we might fly a different vehicle, but at least we can test our code in SITL. So highly recommend using it. Cool. So now to the progress update. So there's this GitHub project in the ArduPilot organization that I've been trying to keep track of all the work. We've got a lot of contributors, so everyone's always curious what's next and what they can work on. So feel free to take a look at the board. Compared to last dev talk, there was, I think, like 20 done issues, and what is that, 100, I can't read it, but 130 something done issues and PRs. So we're really moving quite quickly. And last dev talk, RDPilot was a clock, and now it can actually do autonomy. So I'm pretty pleased with all the updates. So I'll go into some specifics. Feel free to stop me with questions. So the first one is, how do you configure it? So the ROS2 interface, you can disable and enable any channel at compile time with these flags. And then I just added a PR to change the publish rates. So you can basically set your default rates for any channel and enable things. If you're using this in production, I think it's a good idea to disable everything you're not using and only use the data rates you actually need for your platform. So as far as hardware interfaces, we now support, as of 4.5, you can connect your companion computer to your autopilot over serial. We use native Ethernet support on UDP4, and then PPP is also supported. We could do CAN if we wanted, but I haven't had anyone ask me for it. So if you want CAN, let me know, but otherwise we'll probably not do it. And if you're a hardware vendor making combo flight controller and companion computers, Ethernet, please. Thanks. It'd be great if you could set ROS2 parameters or RDPilot parameters on the ROS2 CLI, and was bummed out when I found that MicroROS wants to duplicate all your parameters. But we found a way to do it with MicroXRC EDDS. So that's up for PR right now. You can use the ROS2 CLI to retrieve or set any parameter, and you can crash your vehicle like this, but same as the normal way of parameters. So don't dump them stuff, and be careful what you're setting in flight. There's some limitations with it. There's other CLI commands for the ROS developers you might be familiar with, like ROS2 param list, which lists all your parameters, and param dump. We can't use those because it'll fill up the array size array sizes that we have to allocate in the library, and we don't want to allocate a 2,000 element per struct. It would run out of memory. So we can't support those. And then we did try using MicroROS before, but as I mentioned, it tried to copy there was no way to avoid copying all the parameters, and that was really inefficient. So not really an option. Since 4.5, we've removed this XML refs file. So in the last talk, I showed you how to add a new topic, and you edit this XML document to specify the topics and the quality of service and things like that. So we've switched to the binary entity creation method, which is recommended by eProsima. It basically puts this in the source code instead. Our goal was that you could edit the refs file without having to recompile the code and basically enable or disable topics, but that's not how it ended up being implemented. So now we're just doing it at compile time. I don't really see many people wanting to enable and disable interfaces at runtime. So, but if we wanted to do this at runtime, we could. So instead of the refs file, you can we're surrounding all of our channels in these compilation defines. You can set your topic and the type and the quality of service. And if you're wanting to add a new channel, feel free to talk to me on how we should set those up. As far as the configure and build, this is one of the huge advantages of RDPilot right now compared to anything I've seen, is you can call colcon build and build both your autonomy code and the RDPilot code base at the same time. Challenges with this was, how do we expose all the WAF arguments, because there's hundreds now with all the configure options exposed from build options. So the new thing recently added was the RDPilot WAF configure args and RDPilot WAF build args. So this was a request by Tridge, because we were calling things different names, and he's like, how do I turn on debug mode? And I was like, okay, well, now you can just set these and pass anything into WAF. So there's an example call. If you want to change a configure define to change how fast the global origin was reported to once every 5 seconds, you can do that. So DDS supports exposing some sensor data. New is multi-battery, multi-GPS. There's a couple approaches to exposing when you have redundant sensors. Do one topic for each of them, or make a custom message with an instance ID field, or use the frame ID. After talking to a bunch of community members, we settled on option 3. So you can see here is a printout of a navsat fix message. And so we just set the frame ID to the instance ID of the GPS sensor. So this will use less RAM than option 1. And I'm going to put a note in. I'm not personally interested in writing all the sensor conversions for every driver. As Tridge said, you can just use DroneCAN to get every CAN sensor. So I think that, if you have some other sensor and you want its data and you have ROS, probably just pull in DroneCAN somehow and get it into your application. So for controls, we're trying to basically make a sane API to control vehicles. In the time that I've spent using the guided API with Plane, it's quite difficult to understand which fields apply when. And so ROS is basically trying to just start with the simple stuff and get that working and then move on from there. So the good thing is we have waypoint control working for all the common vehicles. So you can basically, for global positions, so you can send a lat long out and it'll go there. The bad side of the controls API right now, in my opinion, is takeoffing and switching to guided. So it's very vehicle specific. You have to know, it's a custom message that we have for this. You have to know the mode IDs from ROS2. There's not a C++ header you can pull in to define those in your code. And in Copter, you have to call a dedicated takeoff service while Plane has a takeoff mode. And really, you just want to get the vehicle in the air and go to 1 point. So this is sort of just like an annoying thing that, I just want to go tell my vehicle to go somewhere and take a picture of an area. But you have to deal with these complexities in your application and know which vehicle you're on. For navigation, we support, well, yeah, I guess control navigation are a little bit mixed here, but there's velocity control for Copter too, by the way. So for navigation, we support global waypoint control, and Copter and Rover support velocity control and body frame. And then Plane, there's been a bunch of work recently to support some guided primitives to do things like paths, which I'll get into. But we want to support more primitives because this is sort of like one of the focus areas of ROS is doing planning off board and sending where you want to go more than just waypoints. So here's an example of integration with the Navigation 2 stack, which is a pretty widely adopted ROS package in ground robots for, it does a bunch of things, but this is basically running a path planner and integrates well with, it's generating a cost map on the left there. And so this is integrated with the gazebo simulator. There was a talk yesterday on that. So yeah, here's another example of gazebo and Artipilot working together on ROS. And shout out to Pedro for getting this implemented in his GSOC project last year. So I was actually just sent this video 15 minutes ago by someone in the community. So here you go. Here's a 3D, sort of a similar demo, but in 3D. So on the right is a Bonks AI map. So if you're familiar with Octomap, this was presented at last ROSCon and a successor to it. So it's a hierarchical voxel grid. So it's going to allow you to do, this is basically supposedly going to be the new way that if you're doing 3D planning, that you're going to represent your map in. It's a lot more efficient memory-wise. So you can have a really dense grid, but it's sparse, so you don't need to represent every single centimeter of the Earth as occupied or unoccupied. So here's just an example of building up a map in a voxel grid, and hopefully that code gets open source at some point. Right. So, oops. As far as documentation is a big important thing for us. So on the left is the operating systems that we have documented on how to set this up. So Ubuntu 22, macOS, and if you're using Docker, you can do it. And then on the right is sort of like a high-level overview of the tutorials and sort of which wiki pages we have. And then there's a couple videos actually for a lot of the tutorials that show you start to finish running the tutorial. So this is, in an effort to make it as easy as possible to repeat the demonstrations that we've set up. So yeah, and Sankit had put together a nice video for the Plane waypoint follower that I built. So thank you for that. I just added an interface documentation. So this is sort of like in between a message definition document and looking at the source code to figure out how things work. And I've separated it by subsystem so you can see all the sensor data that we expose and sort of how to get the pose of the vehicle. This is just the first draft of the wiki, but I think that this is going to be really useful for people that are integrating with ROS to see what data channels do you actually expose and how do I use it and what are your coordinate systems? And is it a publisher or a subscriber? Yeah. So the next thing, AP Geoid library. Reese worked on this a while ago and just wanted to let the dev team know that we have this. So DDS, the ROS interface that we're using, we want to use the WGS84 coordinates for everything. That's part of the message definitions and not MSL, but the default for ArduPilot, as far as I can tell, is MSL, which is a bit of a problem on certain GPS receivers. You don't actually know which datum it's using, and ArduPilot doesn't keep track of it either. So suddenly try integrating this with a bigger system and your vehicle's at the wrong height. So what we've done is ported geographic lib, which is an MIT licensed geographic coordinate library, into ArduPilot. We download the Geoid data onto the SD card, and you suddenly can convert between some of the common datums. So I'm not sure. So some of the GPSs, well, uBlocks actually does support reporting based on the value of GPS driver options. You can set it to use ellipsoid height. So I didn't know about that until a couple of days ago, but it's not documented in the wiki. So we definitely need to get that on there because this is going to be a huge problem for people integrating with terrain data and other things off board to make sure we're clear on which datums we're on. So anyways, it's on a branch. I'm interested. I'm going to probably bring this to dev call soon to talk about whether we want to merge this. But an example, here's the diagram. So there's geoid height and the ellipsoid. If things are in terms of the ellipsoid, it makes it a lot more portable across the ecosystem. And so if a GPS is reporting in geoid height, we need to know which geoid it is so that we can convert. And on the left bottom is some of the common geoids that geographic lib will support. So now I'm going to get into sort of an application for this. So this is some local pilots where I went to college. They took off from this field here, which is about half a mile from the Coors factory. And two fixed wing pilots took off, and this is their approximate flight path. They basically took off to the north and then went around this mountain, and then they started flying up along the cliff band there because it's cool. So here's a video. Fair warning, I did try to cut the video off, but so basically these are like two park flyers flying FPV kind of thing. They're turning to the right, and as you can imagine, you might start to lose signal, and they went into a failsafe and try to turn towards the hill and do an RTL. So unfortunately, both vehicles actually crashed, but not, they're just small park flyers. No one was hurt. But I think this is like a useful thing to talk about like what can ArduPilot do to help people actually, when RTL happens, how to get the vehicle home safe on fixed wing. Can I go to the next one? Nope. All right, so here's the map. Same picture before. So some options the AutoPilot could do would be to go straight and then turn a left and come back. Or maybe it could gain some altitude first and then climb over the hill and get back. And what the AutoPilot actually did, both of these, was to do a sharp right turn and go straight towards home, which is sort of the naive approach for getting back. And both pilots actually both crashed into the hill because of that. And ArduPilot, there's some things we could do to maybe predict where it's going to be based on the terrain data and maybe turn left instead of right to avoid crashing into the hill. But there's another option you could do, and according to Philip, is add a cube. So basically, we're going to set up the problem statement as you have a latitude, longitude, height, and bearing for where you took off from. And when you lose signal and RTL is engaged, you have the same thing. And you want to find a way to get home without crashing into terrain. So The constraints are for this kind of problem are you have an AGL limit in the US, you're not allowed to fly above 400 feet. We do have access to terrain data. We know our initial and final pose. We have limited battery, so we can't just climb up to the altitude ceiling. It's be a bad idea to do that. We have a curvature constraint because we're on fixed wing, and you can't just go straight home and climb because the terrain might be steeper than your climb rate that you can actually achieve. So luckily, there's a researcher from ETH Zurich, Jay Young, who's implemented a planner that can follow these constraints. So it uses a RRT planner. It's designed for fixed wing and it avoids the terrain and maintains that AGL altitude constraint. It's using Dubin's 3D paths and which are great for fixed wing, and then it applies a curvature smoother because by default, Dubin's paths are not kinematically feasible. And it's efficient enough to run on a Raspberry Pi, and he developed it on a ROS1. And if you want, you can go click the link to the paper when I post the slides in a bit here. So what we've done, Reese is another developer. We put together a port of this planner into ROS2 and integrate it with ArduPilot. So the goal is to provide low altitude navigation in steep terrain. And we're going to start out with this use case of how do we get home without hitting to terrain. So as far as integrating it into Smart RTL, basically the companion computer needs to know when you hit RTL and to be able to plan a route home. And then probably be using something in guided mode to control the vehicle to get home. So here's some other screenshots of sort of like on the right is a top-down view of a Dubin's path. So it's a straight sections connected by curves at your minimum turning radius. And then on the left is the RViz view in satellite terrain of that same path. So this is a work in progress. There's a lot of changes that are needed in ArduPilot to enable this, but the planner itself has been well tested by Jay and his research outdoors on other vehicles, and so I think it's going to be a really good candidate to implement Smart RTL. So other things we've implemented an external control library. So this is to minimize code duplication and handling external commands from either a GCS scripting or DDS. And so some common things you need to do is make sure the vehicle's in the right mode or that it's armed before accepting commands. And so this new library is sort of the central place to do that. And so far, DDS and scripting are using it. And there's only a few functions because it's not a huge API. But I'm looking to basically take Mavlink and pipe it through this and share a lot of the common validation logic to reduce our flash usage. So the library is well tested. So here's an example of the unit tests and the system tests. So the unit tests are just a couple lines of code, and the system test is running the ArduPilot binaries and DDS interface and checking various fields. So this is how, with a pretty small development team in their free time, can maintain an interface like this at a high quality. So other things of note, we can do swarming in Gazebo with this interface. So here's an example that Reese put together with 4 copters with 4 simultaneous simulated cameras. So if you're interested in doing swarming, Gazebo is a great tool to do that. And there's some great examples on how to do that. So in the future, looking forward to building out more control interfaces, particularly in plane to enable Smart RTL. And there's some PRs that Reese put together that we'll be working on getting in. We want to enable people to enable DDS in the custom build server. So Peter's been helping me a lot with that. We're pretty close. And maybe do some fence work. Documentation, the big thing is how do I take my ROS code and put it on my companion computer? That tool chain is super terrible in the open source community right now. It's super confusing. So we're looking together to put a nice documentation together on that. And then, continuing our work with Nav2 to show how to use all these great planners and controllers that people have already developed. And then I'm looking to doing some more FPV flying. So huge thanks to all the contributors. Reese is the other maintainer. He's put a ton of effort into this capabilities and a lot of the demos and mentorship. And then Pedro from last year, who did his GSOC contributions for Nav2. So yeah, and the ArduPilot dev team, thanks for entertaining all my pull requests and questions. Thank you. Maybe two if they're really quick.
Okay, I'll try to be quick. In the smart RTL function, did you consider other cases where it's not necessarily terrain, but for example, buildings or like people that you wanna that don't show in the terrain data, but that you want to
Yeah,
avoid?
absolutely. I think for me, planning is your map is going to hopefully take into account some of these things, and you can use some sensors to build the map live. But we need to start somewhere with some information we already have, and I think terrain's the best thing to start with because the ground's always there. So let's try to avoid that first.
Daniel's asked a lot of questions, so maybe that's one squeeze in front of him.
Sorry, there's a lot of good stuff. All right, main one was this might be a bit adjacent, but have you worked much with like the URDF format in your ROS2 work?
Really, but
Okay. Are they still using it, or is it?
Yeah.
Okay. Oh,
Yeah.
Okay.
Yeah, so
Okay.
the gazebo models, those are all URDF models, and so the props spin just like Pete's web tool. So yeah, I think it's a great tool, but I'm mostly concerned on the
Yeah.
planning side. So yeah.
And then is Reese your gazebo wizard, or do you have like others that you're familiar with that I could ask you about afterwards?
Yeah, he's the gazebo wizard. I've used it a little bit. But it's really just us two sort of maintaining a lot of this stuff. So and we do it on our free time. So,
All right,
the
cool.
responses may be delayed, but we try our best.
All right, thank you.